Hey guys, I have the hiccups, so bear with me. Okay, so infinite series is so there's two different things that an infinite series can do. Either that number is going to get so large uh, or so negative that's going to approach positive infinity or negative infinity. If it does that, it's doing something that we call diverging. So it diverges to positive infinity or negative infinity, depending on what kind of sequence you're looking at. Um, some infinite series, their sums converge. So if they converge, that means they approach one specific number. You might remember when we looked at an infinite series back on our first day of series, I believe it was 3 over 10 to the n, and we figured out that infinite sum was a third. Same sort of idea. So, here's what you need to know. This is super important. So important that Peanut came up here to tell you that you need to pay attention to this piece of information. Here, point to it, Peanut. That piece. Right there. Right there. Only geometric series where the common ratio, the absolute value of that common ratio, is less than 1. That is the only time that a series is going to converge. You can do a little modeling now? Okay, thank you. Only geometric series whose ratios are less than 1 converge. Okay? Cool. So, the sum of a converging geometric finite series is right here. The first term divided by 1 minus the common ratio. So here we go. Determine if the series converges or diverges, then tell the limit. So this first one is written in limit notation. You won't see that very often. I just want you to get the idea that, remember, we can't actually plug in infinity for the term number because infinity isn't actually a number. So really, I'm approaching infinity there, even though that's not really, I can't plug it in. So anyways, so we'll decide if it converges or diverges first, then we'll go through and tell the limit. So right here, since I have something to a power, I know that it is a geometric series, so that's a good sign. Next thing we have to do is look at r. R is the one with the exponents on it. So that's 0.75. 0.75 is less than 1. It's geometric, it converges, or it's geometric, the R value is less than 1, so it converges. Over here, I have 2 to a power, so that means that's geometric again. 2 is my common ratio, but 2 is bigger than 1. So then that's not going to converge, that's going to diverge. Down here, I have 4 times 1/2 to the n minus 1. So that is a geometric series. And R is right here. It's 1/2, and that's less than 1. So that's going to converge. On this last one, that one is also geometric since I have something to a power. My rate is negative 1/2. Negative 1/2, the absolute value of that is less than 1. So that will converge. So then let's go through and talk about these. What does it converge to? So for A, remember, to find out what it converges to, we need to take my first term divided by 1 minus the common ratio, and we decided that was at 0.75. Now, if we go ahead and excuse me, multiply that out. Sorry. You're going to end up with 12. Over here. So my first term, it's diverging, right? And my first term is 4. So we've got 4, and then 8, and then 16, 32, 64, 128. It's just getting bigger and bigger and bigger and more positive, right? So I have a bunch of positive numbers that I'm going to add more positive numbers to. And so since we're doing that, it's going to approach infinity, or it's going to diverge to infinity. Over here on this next one, we know that it converges. So we need to take our first term, which is 4, divided by 1 minus my common ratio, which was a half. Let's see, so 1 minus a half is a half. 4 divided by a half is 8. Over here, you're converging. So our first term was 6, divided by 1 minus our common ratio, which was negative 1/2. So that's plus 1/2. And then when we simplify that guy, we're going to end up with 4. Last one in this example. We have the sum from 1 to infinity of 4 minus 1/2 times n minus 1. Okay, so this time, this one is not geometric. It's arithmetic. Even though the common difference is a half, that doesn't mean that it's now going to converge. It's arithmetic. Remember, only geometric series converge. So since it's arithmetic, that means it's going to diverge. But now let's think about that. So we start off with 4, and then each time we're subtracting a half. So we have 4, 3.5, 3, 2.5, 2, 1.5, 1.5, negative a half, negative 1, negative 1.5. Pretty soon, those positive and negatives are going to cancel each other out, and then I'm going to keep on adding more and more negative numbers. So that means I'm going to diverge to negative infinity in this guy. Oh, right. Now we want to evaluate this sequence in sigma write the sequence in sigma notation, and then evaluate the series. So first of all, I have 9 minus 3 plus 1 minus a third. So I'm multiplying every time. So that's geometric. If I take the second term divided by the first term, so negative 3 divided by 9, that leaves me with negative 1/3 for my common ratio. So what does that common ratio tell us? Does that converge or diverge? That sucker converges. So let's write this in sigma notation. So we want to go from n equals 1 to infinity. This is a geometric sequence, so here's what we know. We write it by 9 times the common ratio to the n minus 1 power. So now that we have it in sigma notation, now we want to evaluate it. So my first term was 9. I'm trying to find s sub infinity. There we go. Times 1 minus, and then put in parentheses, negative 1/3 to the n power. Over 1 plus 1/3. Okay, notice right here, I did do minus negative 1/3 is plus 1/3. That's fine. Over here, I have to take negative 1/3 to a power first. So I have to have minus parentheses negative 1/3 to a power. You can't just put plus there. You're going to get some wrong answers if you do that, so be careful. Okay, so once we pop that guy into our calculator, we're going to end up with 27/4 for our infinite sum there. All right, on this next one, we have 1 plus 3 plus 5 plus 7. Now, I'm not multiplying by the same thing every time. I'm adding the same thing every time. So that means that this is arithmetic. And I'm adding 2 every time, so d equals 2. Since it's arithmetic, it has to diverge, no matter what the common difference is. Now let's write it in sigma notation. So I want the sum from n equals 1 to infinity of. Now, how do we write this for arithmetic sequences? Remember, it's the first term, which was 1, plus the common difference, which was 2, times n minus 1. Now, I'm adding all positive numbers together, right? And from here on out, I'm only going to get more positive numbers. So this is going to diverge to infinity. All right. On this next one, we have 1, 8, 27, 64. We're not really adding the same thing every time. But what you might notice is a similarity between each of these numbers. 1, 8, 27, and 64. Each of those is a perfect square, right? So is it geometric or not perfect square or perfect cube? So maybe it's not geometric or arithmetic, it's neither. But it's not geometric, so we know that it has to diverge. Now let's think about it. Each of these numbers is positive, and each of these numbers is just getting bigger. So I am adding more and more positive numbers to this, so it's going to diverge to infinity. But I forgot to write it in sigma notation. Let me do that real quick. From n equals 1 to infinity of, now each of those was some number cubed, so that's n cubed. All right, so next time we are together, we will learn a little bit about binomial expansion. So hopefully I'll get rid of my hiccups by then. Okay, I love you. Bye.